Morning, students. Today's lesson we shall discuss pulse amplitude modulation and also we shall see TDM-PAM. Now, what is pulse amplitude modulation? Is pulse amplitude modulation we have already learned in first three lessons, where the signal is sampled and converted series of pulses. That means the signal is transmitted in the form of amplitude modulated pulses. That means amplitude of the pulse actually carries the information of the signal value at that particular instant. That is why it is called PAM or pulse amplitude modulation. Of course, it's very theoretical because uh, you must remember that a signal in present day is not transmitted like this. In present day transmission system is quite complicated, but you cannot learn the complicated system right at the very beginning. You have to start from understanding the basic principles. So this is pulse amplitude modulation or PAM, where amplitude of the pulse carries the signal information of the signal value at that particular instant. Okay. Then it is written here, amplitude of the pulse is the measure of the signal value at that sampling instant. This is pulse amplitude modulation. Now we go to TDM or time division multiplexing of PAM. Look, when you do sampling, you not measure the signal continuously. You measure the signal at certain interval. Maybe microsecond, maybe second, millisecond, whatever it is. There is an interval. Now, today you have got very high-speed electronics. What you can do, time in between, you can transmit another signal, samples of another signal. And if you do that, that is called time division multiplexing. It is like, say, this is signal 1, this is signal 2, this is signal 3. And this is receiver 1, receiver 2, receiver 3. On the transmitting side, there is an electronic switch. On the receiving side, also there is an electronic switch. And these two switches are synchronized. Meaning, the moment when the switch is in line 1 of the transmitter, at the time the switch is in also line 1 of the receiver. So at that instant, the signal of the line 1 or signal 1, sample of the signal 1 is given to the first receiver. Next instant, the switch shifts to channel 2. So within the channel, what flows are the continuous signal value samples. The first one is from channel 1, then channel 2, then channel 3, then again channel 1, channel 2, channel 3, then again channel 1, channel 2, channel 3, like that. And the switches control the whole. And this is what we are doing. We are utilizing the time gap between two samples. And that is why it is called TDM or time division multiplexed or time division multiplexing. And the signal is a PAM signal. So we call it TDM-PAM. Then one important issue is what is the bandwidth of the channel required. Say, what I mean here, channel bandwidth is, say you are transmitting voice signals, right? And say each voice signal is limited to 10 kilohertz, right? Now, if you transmit three such voice signals by time division multiplexing, then You are sending it to a channel, and channel can be, for simplicity today, let us consider the channel is a cable, is an electrical coaxial cable. Then what should be the bandwidth of that cable to transmit three signals time division multiplexing? That is the question. By the way, what is bandwidth of the cable? You must have heard Cat 5 cable, Cat 3 cable, Cat 6 cable. Say Cat 6 cable has a bandwidth of say 10 megahertz. It means cable is so designed, its practical design is so that the cable can carry signal up to 10 megahertz frequency. If the frequency of the signal is more than 10 megahertz, then the signal will be distorted. So that is called channel band. Now, in our day-to-day use, channel is not only a cable. The entire electronics on the receiving side, on the transmitting side, and the microwave transmission, everything, whole thing, all included is the channel. This channel, what is the channel bandwidth to send a TDM-PAM signal? That is the question. Now, let us say bandwidth of the original signal is FM. As I said, say 10 kilohertz. Then, if the baseband signal is amplitude modulated, like you have heard, you have learned in analog communication, if it is amplitude modulated, instead of going for digitization, if it is amplitude modulated, then this is the amplitude modulator. What do we do? You must remember there is a carrier frequency, and there is a signal, and there is the amplitude modulator, and there is a modulated output. And this is the baseband signal. And this is the frequency spectrum of the baseband signal. The signal, there are components up to FM, and various frequency components has got various amplitudes. Then output is just multiplication, so that, as I said earlier, output is a product of two sinusoids, say cos A and cos B. So output will be FC. So say, consider the frequency component FM. FM, when it is multiplied with FC, cos FM when it is multiplied by cos FMT, when it is multiplied by cos FCT, it produces FC, it produces this component, FC plus FM component, and also it produces a FC minus FM component. But both sidebands, they carry the same signal, so practically we use only one sideband, right? So let us consider we are taking the upper sideband. Then this signal, or the basic signal, has a bandwidth of A0 to FM, and a modulated signal will have a bandwidth of FC to FC plus FM. So bandwidth is still FM, but it is shifted to FC. So it is, signal is amplitude modulated and only one sideband is transmitted, then also bandwidth requirement is FM, though it is centered at the carrier frequency FC. So if you send one signal, one baseband signal band limited to FM, you need a channel bandwidth of also FM, but at a higher frequency. Say your FC is 1 megahertz and your baseband signal is up to 10 kilohertz. Then you need a channel 1 megahertz to 1 mega plus 10 kilohertz. This is the channel you need. This is what you do. This is when you do amplitude modulated. But when you do PAM, then what happens? And okay, in modulation, if you do frequency multiplexing, frequency division multiplexing, then what happens? You have got M1, M2 up to AMN, n different types of different signals, but all are band limited to FM. Then you use n number of carriers, FC1, FC2 up to FCN. So first signal produces a band of FC to FC plus FM, and you choose FC2 equal to FC1 plus FM. So it produces a band of FC2 plus F from FC2 up to FC2 plus FM, and you choose FC3 as FC2 plus FM. So this way, for n number of channels, you need n number of FM. That means your total bandwidth required of the channel is n FM. Clear? Instead of digitizing, if you do analog communication and with frequency division multiplexing, if you send n number of baseband signals of each band limited to FM, then you need a channel of bandwidth n multiplied by FM. That means if you have 10 signals, you need 10 FM. Fine. Now let us see what happens if you do digitization. Right? Signals. Here the signals are converted to train of amplitude. Channel is carrying M1 signal pulse, and once again another next pulse of the M1 signal. In between, he is carrying M2, M3, etc., etc. First pulse is a sample of signal 1, and here also again the second sample of signal 1. In between, there are pulses of other signals. Then, now let's go to a little bit inside the system. This is a rectangular pulse. All these pulses are rectangular pulse. In time division, this is the x-axis is a time scale. So this is a pulse, right? This is a pulse, xt. This is a time scale, and say pulse width is tb and pulse amplitude is a. If you take a Fourier spectrum of this, it becomes a sync pulse, and x-axis becomes the frequency axis, and y-axis becomes the amplitude of that particular frequency component. Sync pulse, if you remember, in communication engineering, we consider sync pulse as sine pi x by pi x, whereas sine x by x, we call it sampling pulse. Anyway, so you see, this function, this frequency conversion, this Fourier conversion is infinite. Although the amplitude component, amplitude reduces, but theoretically it is infinite. Means a single square pulse contains infinite frequency components, though maximum is the DC component, zero frequency, and the amplitude of higher frequencies very quickly dies down, but theoretically it has got infinite frequency components. If this is A, if in time domain its amplitude is A and width is TB, time TB, then DC component is ATB. And the sync pulse, it has got first null here, that means first zero here is at a frequency of 1 by TB. This is also at a frequency of 1 by TB, right? Example, say the width of this pulse is 1 microsecond. If it is 1 microsecond, width of the pulse is 1 microsecond in time domain, then in frequency domain, 1 by TB is 1 upon 1 micro, that means 1 megahertz. That means first null is up to 1 megahertz. Now, practically, we have to always, of higher frequencies we shall filter out, but to have enough strength of the signal, we always take the signals up to at least 1 by TB. That means up to at least first null on left side and right side. right? So, pulse, and hence the train of pulse has infinite bandwidth because each pulse has got infinite frequency components. So the channel you need of infinite band, but you cannot buy a infinite bandwidth channel or cable from the market. That will cost you million and million dollars. So you have to save money in buying the cable also. So what do we do here? A practical bandwidth is finite. If you buy any cable, if you buy even the costliest cable, its bandwidth is finite. The cable manufacturer will define that its bandwidth is 1 gigahertz, 10 gigahertz, whatever it is. Let us say that bandwidth is given as W. And then let us find now what is the minimum acceptable W or bandwidth of the cable for transmitting my pulses. Unless you know the value of W that you need, you cannot go to market and buy any cable. So we are going to find that out. How do we do? Let us say the channel you have purchased is ideal band limited channel. That means the function is 0 from minus W to plus W, and the moment the signal frequency crosses W or minus W, it drops down to 0. Let us say your channel is the ideal band limited channel. In that case, whenever the channel is band limited, a rectangular pulse will expand in time domain at the receiving end. A fact. If your pulse is rectangular here and you pass it through a band limited channel, the output of the channel will become in time domain like this. That means the pulse will expand infinitely. Pulse will expand infinitely like if in time domain it is rectangular, in frequency domain it becomes a sync pulse. Similarly, if the channel frequency domain is like this, then when a rectangular pulse passes through the channel, it expands infinitely. And its first null is 1 by 2W, second null, and this side also minus 1 by 2W. And mind it, this is the time axis. That means for rectangular pulse, which right hand was 1 by 2 TB, will become now, first null will become now 1 by 2W, second null at 2 by 2W, and it will go infinitely. That means you have sent a square pulse through a cable, but on the receiving side, he finds there is no square pulse. He finds all are sync pulses. He is in a problem now. If there are series of sync pulses one after the, that means this series of rectangular pulses will appear to be will be series of sync pulses at the receiving end. It's like this. There are two sync pulses at the receiving end. But you should design your system in such a way that in time domain, the peak of the second pulse is coincides the first null of the first pulse. Why? Because what the receiver will do, sample and measure these pulse heights. So receiver will measure it at 0 and at the first null. And if it measures at the first null, then it is the amplitude of the second pulse, and the amplitude of the first pulse is 0 now. Obviously, such expanded pulses should be so placed in time domain that the null of one pulse coincides with the center of the next pulse. That is right. If you do that, then If you arrange in such a way that null of the second pulse coincides with the sorry peak of the second pulse coincides with the null of the first pulse, and then you do sampling or measurement at each peak, then you are out of problem. Otherwise, there will be a problem. Like this, if the pulses are closer, then when you are measuring the second pulse, the some residue of the first pulse also will be added to your measurement, and you will have a problem. So you have to arrange in such a way that the any pulse peak, its peak falls in time domain on the null of the earlier pulse. It's like this. And if you make it further away, suppose the peak of the second pulse falls on the second null of the first pulse, then you are only wasting the bandwidth. And bandwidth is very, very costly nowadays. Crores of rupees are the cost of each megahertz of bandwidth. So we have to adapt this situation. If we adapt this situation, so optimum gap between two pulses must be 1 upon 2W. And what is W? W is the band limitation of the channel or the cable that you have purchased from the market. So if the gap between two pulses is 1 by W, then the gap for n pulses is n by 2W. So gap between n pulses should be n upon 2W, right? That means this is in time domain. This is first pulse of the first signal M1, and then second pulse, second signal, third signal, like that, nth signal, and again this is first signal, right? So in TDM-PAM, n pulses required 1 by 2 FM that we have already found. Requires n pulses gap, needs a minimum gap of 1 by 2 FM because if the sampling rate is, we have seen the Nyquist criteria, sampling rate is 2 FM. If the sampling rate is 2 FM, then the distance from first pulse of a particular signal to the second pulse of the next signal, second pulse of the same signal is 1 by 2. So this distance 1 by 2 FM should be equal to n upon 2W because both are in time domain. If 1 by 2 FM is n by 2W, we find W is equal to n FM. That means W, the bandwidth of the channel, is equal to n times the baseband FM. If you take a numerical example, if you have a voice signal, if you have all voice signals, all of them are 10 kilowatts band limited, and you have 100, or if you and you have 100 such voice signals to be multiplexed, then 100 multiplied by 10 kilowatts, that is 1000 kilowatts, you need a 1 megahertz bandwidth channel. And we found earlier, if you do frequency division multiplexing in analog communication, then also you need the same frequency band of NFM. That means the conclusion is by doing digitization and TDM-PAM, you are not losing bandwidth. You are neither gaining bandwidth. In analog communication frequency division multiplexing, also you need NFM bandwidth. In TDM-PAM also, you need NFM bandwidth. You do not need, some people may have an idea that if you go up to digitization, I need a higher bandwidth. It's not so. The same bandwidth, you can send same number of signals. This is what is called TDM-PAM. In Now we have seen how to create pulses, how to multiplex the pulses in time division or in frequency division, what is the bandwidth requirement, and next in our next lesson we shall go to different. We shall get to the next concept where you say you are sampling the signal. The analog signal can have any value, any value. The value can be 5.003946 millivolt. It can have any value. But in a digital world, we have some limitation in considering any value of the signal. So, how do we tackle that problem? That we shall see in our next lesson.